Today we are going to talk about area between curves. In Calculus 1, you talked about the idea of the antiderivative, which is what takes you back to the original function after you take the derivative. So you learned about the antiderivative first, and then you began to make connections. You started with taking the approximation of the area under the curve using Riemann sums. These strips or rectangles under this curve give you an approximation for the area under the curve. Sometimes that approximation was an underestimate, sometimes it was an overestimate, and sometimes it was hard to tell because some of them were under, like these rectangles on the left here, and then at times the rectangles would go over. So the approximation was with Riemann sums. And as you discovered, the rectangle width or thickness can change. It may start as a more thick rectangle, and then it may change to be something that's a little more thin. And as the rectangles get thinner, you'll need more of them to fill up the space under the curve. And that means that as your rectangles are getting thinner, the number of rectangles are becoming infinite. This brought in the idea of a limit. So as the rectangles got infinitely thin, or small strips, you began to get the true area under the curve. And then a connection was made. To get the true area under the curve, you take the integral. So the true area is the integral, and you had that special integrand symbol. And that was a huge idea you talked about in Calc 1. Today, we're going to take that big idea and build upon it. We're going to merge the idea of not just one curve, but two curves, and try to find the area between those curves. So we're specifically trying to find the area between this red line and this blue curve or parabola. So how would we go about doing that? Well, we're going to have to use the idea of subtraction. The big idea is if we take the area underneath the larger curve, or the one that's above, in this case the linear function, and we find the area of it all the way to the x-axis, and then subtract out the area of the lower curve, in this case the parabola, it will leave us with just the area between the curves. It's the yellow area between. So we would have the large yellow area and subtract out the blue area. So the green that's now on the screen would be gone, and you'd be left with the yellow region. And the yellow region is what we're looking for. So let's talk about the theory here. Here we have a picture. We have an upper curve, f of x, a curve that's beneath it, g of x, and it looks like we're trying to find the area between those two curves from A all the way to B. So you could start with using rectangles and using the approximating rectangles. This rectangle is going from the red curve, f of x, all the way to the blue curve, g of x. So it's showing you the curve on top, and it's drawing a rectangle all the way to the curve on the bottom. So it's showing you the direction. And the theory is, in this red box here, as stated, the area A of the region bounded by the curves f of x, g of x, and the lines x equals A and x equals B, where f and b are continuous, and f of x is greater than or equal to g of x for all x in the domain, is the integral from A to B of f of x minus g of x. So in more simple terms, if you're trying to find the area between two curves with a function on top, f of x, and a function on the bottom, g of x, you're finding the integral from a to b of your top function minus your bottom function. So, when you're dealing with vertical strips going from top to bottom, you're doing things in terms of x. So when you have vertical strips, this is when you're doing things in terms of x. The strips that you draw must go from one function, let's call this f of x, to the other function. We'll call it g of x. Something to make note of. This is a caution. You do not want to have a strip starting and ending on the same function. Should that happen, you need to try to approach the problem in a different way. We will see that in a couple examples. So our caution here is that strips cannot, I'm going to underline that, start and end on the same function. So it can't start on f of x and end on f of x, for example. Okay. So now that we've talked about what this general idea is, let's go back up to that preview question and actually do this one together to see what it would look like. So in this example, we have our top function, I'll call this f of x, and we have our bottom function, we'll call this g of x. F of x is the linear function, and it's written here. It's a little small, so I'm going to rewrite it. F of x is our linear function, x plus 3. And g of x is our parabola, or quadratic function, x squared plus 1. And we are trying to find the area between the two curves. So what we would need to do first is determine where our boundaries are. So our boundaries in this case are the yellow points here. One's on the left and one's on the right. These have been pointed out for us. Sometimes you're going to have to actually find the intersection points, and we'll do a couple of examples with that later. But for now, our lower curve, or our lower bound, excuse me, is going to be this x equals a, and so it's going to be the x value negative 1. That's where the two curves meet on the left. And our upper bound is going to be x equals 2, because that's where the two curves meet on the right. So notice we're using our x values as our upper and lower bounds. We're not using any y's here, and the reason is because we're doing things in terms of x. Okay, so with this example, my strip would go from my top function to my bottom function. So there's my vertical strip. It's reinforcing the idea that we're doing things in terms of x. So then we would set up our integral now that we know where our bounds are. Our integral would go from negative 1 to 2 for our a and b. And remember, we're doing our top minus our bottom. So our top curve was our linear curve, and our bottom curve was our quadratic curve. When you're subtracting, be sure to put that bottom curve in parentheses, because you want to make sure to subtract the entire function and not just the first term. So sometimes that negative will need to be distributed. And that's what we're going to do in this case. So we're going to take this and try to simplify this a little bit. So we have our a, and we're going to rewrite it. So it's going to go from -1 to 2, and we have x plus 3, and then I'm going to distribute that negative through. So negative x squared and a -1. So I've taken care of the distribution. I'm going to simplify it again because it will only make our antiderivative a little easier by combining those like terms. So we're still going to write the integral symbol because we haven't taken the antiderivative yet. And this is going to become negative x squared plus x plus 2. And notice again, I'm putting everything in parentheses to show that we're taking the antiderivative of all of that inside the parentheses. So then we're going to actually take the antiderivative now. This should be a review of Calculus 1. So you are adding to the exponent and dividing by the new exponent. So in this case, this exponent of a 2 is going to become a 3. And so it's going to become a -1/3 in front because we divided by 3. And you do the same all the way through. So plus 1/2 x squared plus 2x. And then we need to evaluate it at our upper bound and then subtract the evaluation at our lower bound. So when you're doing this, it would be -1/3. You do the 2 first, our upper bound. So 2 cubed plus 1/2, 2 squared, plus 2 times 2. And then when you're subtracting the evaluation at the lower bound, make sure you put everything in parentheses to show that you are subtracting the entire evaluation. So -1/3, -1 to the 3rd power, plus 1/2, -1 to the 2nd power, plus 2 times -1. Okay, so now we need to do some math and simplify this down. So this would give us -8/3 plus 2 plus 4, and then minus 1/3, 1/2, and a -2 in parentheses. So then we would distribute, combine all of these values to get 9/2. Now this answer, 9/2, has a meaning, and that meaning is the area between the two curves. So because we're talking about area, we would write units squared. And again, you definitely need the squared there because you're talking about area. So units squared. If the question ever, or the problem you're working with, ever has units in it, let it be centimeters, inches, then you would of course have centimeters or inches squared. But because this wasn't specified, you can just write units squared. So squared units because you're dealing with area. Okay, so that's pretty much the process for how to go through this, but the process is also described for you step by step below. So to review, you need to draw the graph as accurately as possible. This helps give you a visual picture of what's going on. It will also help you determine which is your top curve and your bottom curve. And when you draw the picture, I do want you to show the strip going from the top curve to the bottom curve, or from the one curve to the other. Then you need to find the intersection points if necessary, unless they're giving you some other boundaries. This will be your a and b values for your integral. So you'll set the equations equal to each other if you need to find the intersection points and solve for the variable. And then last but not least, you'll set up your integral. You'll go from top minus bottom if you're doing it in terms of x. So let me write that down. So this is when in terms of x, and you would do right minus left, because you know we always need to switch things up a little bit. So you can also do things in terms of y, and so when that's the case, you'll do it as right curve minus left curve. So this is when you're in terms of y. Okay, so when you're drawing your strips, if the strips are vertical, everything should be in terms of x. This is kind of a helpful little note for you. And if the strips are horizontal, everything should be in terms of y. So make sure to pay attention to the direction of your strips, and that can help you determine what variable your integral should be in terms of. Now let's do a few examples together. So in example 1, it states to find the area of the region bounded above by y equals x squared plus 1, bounded below by y equals x, and bounded on the sides by x equals 0 and x equals 1. So what I did here is I put a little coordinate plane in our notes here so that I can draw a somewhat accurate picture. My drawings aren't exactly accurate in terms of straight lines, but we will try our best. So the first step of the process, as outlined above, was to draw a picture. So we need to draw the two lines that we have here. The first line is x squared plus 1. And I know that that's a parabola that has been shifted from the origin up 1 unit on the y-axis. So I am going to draw that parabola as best I can. The second curve we have is y equals x, and I know this is a linear equation with a y-intercept of 0 and a slope of 1. So I'll be honest, straight lines on the computer are a little challenging. So we are going to focus and try to get them as straight as possible. Now, we have both of our lines, well, one line, one parabola drawn. And so now we need to think about the boundaries. The boundaries that were given to us were, and I'll do this in orange maybe, x equals 0, so that is a vertical line. So here's this first one. And our second one, so I'll write x equals 0. And then our second one is x equals 1. So another vertical line. And this is x equals 1. So you can now see the region that we are looking to find the area of. It's this lovely kind of rectangular with this curve to it region that I'm shading in gray. I would suggest shading the regions lightly on your paper so that you can clearly reference that and not have to constantly think about or locate the region that you're trying to find the area of. So now that I have the region drawn, I need to draw my strip. And my strip is going to show what I'm doing this in terms of. So it needs to go from your top curve to your bottom curve. So there is my strip. It's going from my top curve, which in this case is the quadratic, and it's going to the bottom curve, which in this case is the linear function. So there's the vertical strip that I have. So I have now done step 1 of the process. So I will label this as step 1. Step 2 is to determine your boundaries. Now, many times your boundaries are the intersection points. In this case, that's not true. They gave us the boundaries of x equals 0 and x equals 1. And so the boundaries are going to be those vertical lines. So I'm going to write the boundaries as x equals 0 and x equals 1. So step 2 is pretty simple for us. Step 3 is setting up your integral and actually doing the integral to find the area between the curves. So remember, your integral is going to be from your lower bound, in this case 0, to your upper bound, in this case 1, of your top function, so I'll call this top f of x, minus your bottom function, I'll call this bottom g of x. And we are going to be doing this in terms of x, so we'll put the dx there because we have a vertical strip. And that vertical strip is reinforcing the fact that this should be done in terms of x. So let's determine what our top function is and what our bottom function is. Our top function is the parabola, so that would be the function x squared plus 1. And our bottom function is the linear function x. So we're subtracting x from the parabola. So there it is set up. Now I'm going to rearrange this to try and make it go in decreasing order of exponents. I personally like to do it that way. So from 0 to 1 of x squared minus x plus 1 dx. So now I have my integral set up and ready to go. So I'm going to take the antiderivative and then evaluate it at 1 and subtract the evaluation at 0. So you will have 1/3 x cubed minus 1/2 x squared plus x, and then we need to do the evaluation. So we will do 1/3 times 1 to the 3rd power minus 1/2 times 1 to the 2nd power plus 1 minus the evaluation at 0. Evaluations at 0 are nice when dealing with polynomials because many times the terms will cancel out. So if I were to plug a 0 into this first one, that would equal 0. The second term would also equal 0, and the third term would also equal 0. So we are really just subtracting a 0 off the end, which really isn't subtracting anything. So then we will simplify this to get 1/3 minus 1/2 plus 1. And this will give us the area of 5/6 units squared. So again, you're drawing your picture. You are trying to be as accurate as possible. Make sure to draw your strip so you know what you're doing your integral in terms of, x or y. You'll then find your boundaries. In this case, since we're doing them in terms of x, we use the x values 0 and 1. And then we would set up the integral and find the area. So that is how you would do the area between two curves. Now that we've looked at example 1, I'd like to look at example 4. This is going to show us how to find the area when in terms of y. So above example 4, there is a theory, and it states, some regions are best treated by regarding x as a function of y. If a region is bounded by curves with equations x equals f of y, x equals g of y equals c, and y equals d, where f and g are continuous, and f of y is greater than or equal to g of y for c to d, then its area is the integral from c to d of f of y minus g of y. So this is giving you an example of when you're going to do the integral in terms of y, because your functions are written as x equals, and you're going to really, let me get my color here, do this from right minus left. So you'll take your function on the right and subtract your function on the left. Again, I want to point out that your function must be written in terms of y. What does that mean? It means that you've solved it for x. So you'll have x equals equations. Notice in this picture here, we have x equals equation. We have y equals c at the bottom. That's our lower bound. Our y equals d on the top. That's our upper bound. And my strip is horizontal for this shaded region we want to find the area of. That's reinforcing the fact that you need to get your equations in terms of y. So this delta y here is the width of our rectangle, and it's a horizontal rectangle, so therefore we're doing things in terms of y. The process is pretty much the same as what was described above. Again, we're just doing the equation on the right minus the equation on the left. Again, you're having horizontal strips. So this is when in terms of y, okay, so that delta x is showing the width of your strip. And so let's see what this looks like. This is going to be a little different. We're going to have to use technology to help us really figure out what this picture is going to look like, but I think that we can do it. So to begin, it says example 4, find the area of the region bounded by the curves x equals y squared minus 4y and x equals y minus y squared. So I can't, off the top of my head, really figure out what this picture is going to look like because it is in terms of y. So we are going to use technology to help us. We're going to graph in terms of y. There is a way to do this on your graphing calculator, and I will show you how to do that. The steps for graphing are written as follows. You would start with clicking on Mode and changing it from function to parametric. Step 2 would be to change your equations in your calculator. The y equations, y1 and y2, would have the variable t, and the x equations would represent the equations that we have in our problem. Now notice the way in which they're written in the calculator is using the variable t. That's because we changed the y to be t's. And so really they are representing the equations we have in our problem. It's just written with a different variable. So this first one would really represent the y squared minus 4y equation, and the second one would really represent the y minus y squared equation. Once you have input the equations, to graph it, you would click on Window and start with your standard graph and then adjust your window as needed. So let's try this out. Turn your calculator on and go to Mode. Arrow down to where it currently says Function and arrow to the right to get parameter, PAR, and select it by hitting Enter. Then go to y equals and input the equations as we have written. So x1 is going to be t squared minus 4t. y1 is just t. And again, to get the variable t, you're clicking your variable button, xt, and so forth. So it's just clicking the variable button like you always have. x2 is t minus t squared. And y2 is just t. So then I'll select Window, and you can change your parameters. You can also do Zoom and hit Standard 6 if you'd like to start that way. So there's the general picture that we have going on here. You can tell that there are two parabolas. One is going on this way, and the other is facing this way. So that's the general picture I need to sketch. So I'm going to do a very liberal sketch here. So it's going to be not super accurate, but enough to give me the general look. So one of my equations is going to be going this way. Extend it out. And the other equation is going this way. Okay. So this is my x-axis, my y-axis, and I'm going to shade the region that we're talking about here for the area between the curves. So there's my region. Again, it's a very general sketch. I'm going to bring the calculator to show you how it does kind of match up. It's not perfect, but I certainly tried. Okay. So now we need to match up our equations with our picture. So this first equation, let me get my pen. This equation that's upside down here, this sideways U, is x equals y squared, y squared minus 4y. And this equation down here is x equals y minus y squared. So we now have that. One thing we do not have is the intersection points. So we do not know where these two lines intersect, unlike the example we did before. So we do need to find the boundaries on this. So to find the boundaries, our directions in the very beginning said to set your equations equal and to solve for the variable. So we are going to set our equations equal, y squared minus 4y equals y minus y squared. And then we are going to bring all of the variables to one side. So 2y squared minus 5y equals 0. And then solve for the variable. Now this one, of course, can be factored a y out. So 2y minus 5 equals 0. So it's showing us that our boundaries are 0 and 5 halves. Now that we know our boundaries, we do need to draw our rectangular strip to show our upper and lower curve. So our top curve here is going to be on the right, and our bottom curve is going to be on the left. So when you're doing things in terms of y, you want to reference it in terms of right and left. So our top, or our right, is going to be on the right-hand side, and our rectangle will go all the way to the bottom, or in other words, our left. And that will help us draw our integral. And that is the last step, to set that up. So the area is equal to the integral from our bounds of 0 to 5 halves. And then again, we need to do our right function minus our left function. And this is going to be in terms of y. So our right function, when we're setting up our integral, is the upside down parabola. So it's the y minus y squared. So y minus y squared minus, and again, always put the second one in parentheses, so you subtract the entire function, minus our U-shaped parabola, sideways U, which is y squared minus 4y. So y squared minus 4y. And notice it was actually not too bad to determine which was on the right and which was on the left, because we labeled them when we graphed them. So this one that's on the left-hand side we labeled, and the one that's on the right. So it's much easier if you label them when you're graphing, so that you don't have to figure it out again when you're trying to set up your integral. Okay, so now that we have it set up, we just need to distribute the negative through, simplify, the integral and then take the antiderivative. So let's do that. So we have a is equal to the integral from 0 to 5/2, and then that would simplify to negative 2y squared plus 5y dy. And then we would need to take the antiderivative from there. It's going to become negative 2/3 y cubed plus 5/2 y squared. And then we would need to evaluate it at our upper and lower bounds of 5/2 and 0. And so when you do this, you would get negative 2/3 times 5/2 to the third power plus 5/2 times 5/2 to the second power minus, and again, notice this is a cubic here actually because the exponent's a 3. So when we plug our 0 in the first term, it's 0, and our 0 in the second term is 0. So we're really just subtracting a 0 off of this one. And so our final answer would be 125 over 24 units squared. And that is the area between the two curves, and this time those curves were in terms of y. So I hope now that after going through an example in terms of x and an example in terms of y, you're able to see how to find the area between two curves in respect to x or y, and hopefully you'll be able to get through the first part of your homework. The questions and examples that are remaining will be touched upon in class, and we will go through them in more detail, whether as a class or in your individual groups. So until we meet again, good luck and take care.